Hi, I'm Ben-Yaakov. This presentation is entitled Decoupled Inductors or Ripple Steering Filter. A recent article in Bodo's magazine showed this circuit here. This is a power supply built around two modules of isolated DC to DC converters forming a plus minus 5 volt. There is an input filter here, there is an output filter here, and what is interesting is this element here, which I'm showing here because this is blurred, and you can see that there is here a coupled inductor. So this is a coupled inductor filter or ripple steering filter, and this is the subject matter of this presentation. The idea of this filter, this coupled inductor filter, it really dates back to 1933. There's a patent here, and here it shows this filter. You see there is an inductor, this part is coupled to it, and here is a capacitor. So this is basically this idea of the coupled inductor filter. Until 1999, I guess nothing much has been done with this filter. In 1999, Hamil and Crane, in a paper that is considered the first academic study of this filter, showed the filter and then analyzed it and showed its performance. And they have shown that when you consider the filter an open circuit, here, this is the input, say, this is the output, then you can describe it as a T network. This is LA, LB, and LC are, of course, related to this element, to the inductances and the coupling coefficient. When you look at this equivalent circuit, you realize that indeed, at resonant, LB and C, here we're going to have about zero ideally, and therefore there'll be a blocking of the ripple from here to here. So it'll be like a perfect filter. They've also found that for this configuration, the condition for the zero, which is a notch, is that the K, the coupling coefficient, should be the square root of these two inductances. LAC is this one and LDC. However, in practice, we need to have a capacitor and we are going to have a load. Otherwise we don't need a filter. And therefore, the situation is much more complex. If I look at the coupled inductor, the fact that K is smaller than 1 and that you have here leakage inductances, magnetization inductance, and this capacitor, these relationships are really complex. There have been some papers that derived equations that describe this behavior, but really, until you plot it, there's nothing much you can tell from the equation. And we can do the plotting by simulation. And this is what I'm going to do in this presentation. So I'm going to study this filter by doing some LT SPICE simulation to see what is the behavior and what can we expect from a filter like that. So here is the setup. I have really three cases. This is the basic filter. These are the coupled inductors. I'm starting with C equal to 10 microfarad. This is like they have in the paper of Hamil and Crane. C out 0, that is just a resistor, and this is also a condition they had. And the coupling coefficient of 998 according to the relationship that I've shown earlier. And now I have also here a backward condition, that is the excitation is here on the right rather than on the left here, and the load is here. And here I'm comparing it to a very simple LC filter where the L is the same inductor, same inductance, and just a filter by itself, no coupling and no resonant here. So this is the conventional filter. And here I'm doing AC analysis to see what is the response of this circuit. And here are the results. I'm showing here, first of all, the response of the simple LC filter. I should say LR filter because there is no capacitor here. but this is the simple case without any coupling. And this is now the coupled inductor response. We see here the notch. This is the resonant point. And we see also the backward response, which also shows some notch here, but as you can see, the attenuation here is minus 54, and here it's much larger. So obviously the forward direction is preferred as far as the attenuation goes. If I'm adding 1 microfarad output capacitor, which I should, because I wouldn't use a filter like that without an output capacitor, then I see that first of all the notch attenuation becomes smaller. We see here the notch. And now we see the LC response. Now we have a capacitor. And the difference here is only about 20 dB, and this is for the parameters that I've used. Okay? Backward is something similar to that, but let's concentrate on the forward response. Now, as it turns out, the most important parameter in this configuration is the coupling coefficient. So therefore, I'm going to run now a simulation stepping the coupling coefficient from 0.8 to 0.99 with the steps of 0.02, just to see what is the effect of this coupling coefficient on the response for this particular setup, that is 1 microfarad this capacitor and 10 microfarad this capacitor. I'm concentrating now on this response. So here are the results. We see that indeed there is a big change in the response depending on the coupling coefficient in terms of where is the resonant and also the attenuation. Now this is not monotonic. I mean, it's not goes like from 0.8 to 0.99 this way, but it goes this way and then back. So in order to concentrate on a region that could be of interest, I've run a simulation around 0.96, which shows now the response for 9.4, 9.6, and 9.8. You see that the frequency is changing, the attenuation is changing. Now 0.98 actually lost the notch. So therefore, I run it again around 0.94, here it is, and I'm comparing it to the LC response. Okay, so this seems to be a good operating point, 9.4. We see that at the notch we have quite a bit of attenuation for this particular frequency as compared to the simple LC filter. But if you take into account that there could be a change of plus minus 1%, and this is about the change here, then you have uncertainty, and you can say that this is the attenuation that is assured with a change of, say, plus minus 1%. And here I'm seeing something like 20 to 30 dB, depending, of course, how you define this margin here. So what we can say is the following. For this set of parameters with a coupling coefficient of 0.94 plus minus 1%, you get an additional attenuation over a simple LC of about 20 dB. And that is what it can provide. Now, what about the sensitivity to this capacitor, the resonant capacitor? We talked about the coupling coefficient. So now I'm going to change this capacitor, stepping it from 1 microfarad to 1.5. And we can see that the sensitivity is rather low. That is, we can tolerate quite a bit of a change in the capacitor. This is a large change. And the attenuation will not change much, or the inaccuracy or uncertainty is not that much, and you can get quite a bit of an attenuation. So this capacitor is not that important as the coupling coefficient. So now comes the question, can we use this in a buck converter in order to steer the ripple from the main inductor into this bypass? And this has been suggested also in the paper of Hamil and Crane. So what I'm doing here, I'm comparing the coupled inductor filter to the simple operation of a buck converter. Now the operation of the switches now is here emulated by a source that produces a square wave, okay, with a duty cycle of about 0.68. First of all, I'm running an AC analysis to tune the operation of the switching frequency to the notch frequency. In fact, I have run it and looked at this notch frequency and then adjusted the switching frequency of the buck converter to be equal to this frequency. And here are the results. This is the ripple of the main inductor of the coupled inductor filter. It's about 2.5 milliamp peak to peak. This is now the actual ripple of a simple buck converter, and it is 80 milliamp. So we have quite a bit of a saving here. So we have quite a bit of an attenuation between the simple one inductor and the coupled inductor. This is again the coupled inductor as compared to the actually ripple of a simple buck converter. So indeed there is quite a bit of attenuation of the ripple. However, we are exactly at the notch. And of course the question is, what happens if you move with the frequency from the notch due to a change, say, in the coupling coefficient? And here I've changed the coupling coefficient from 0.96 to 0.95, which is about 1%. And you see already that the ripple went up to 11 rather than 2.5 milliamp, okay? So you can see that the sensitivity here. And to look at it a little bit better, I have run a performance analysis type of simulation in which now this is the coupling coefficient and this is the ripple of the coupled inductor filter. This is one-sided ripple, peak value, and this is the simple LC, simple basic buck converter. So here we have 40 milliamp peak current ripple, and at the notch, of course, we have very, very little ripple in the coupled inductor. Now, if we again assume a plus minus 1%, we see that we can have a change which will, at the worst case, still give us this attenuation. This is now a linear scale, so it is between 40 to say 8, so it's 5-fold. It's not that much. And the question is, of course, if it's worth it. So what are the conclusions here? The coupled inductor indeed exhibits a notch response, no question about that. But it is highly sensitive to the coupling coefficient. And it would seem that about minus 20 dB attenuation can be expected in practical circuit when you compare it to a simple LC filter configuration. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.